We're going to have a look here at how taking the ln of a function affects the graph of that function, and then what the graph of ln of that function is going to look like. This, I believe, is technically just on the outside of the Stage 2 Mathematical Methods course, but I think it's so useful as a way of exploring some of the properties of ln of x and some of the properties of functions that I think it's really a useful thing for us to do. This is something that may appear in a test and has appeared in past tests, but is not part of the examinable content of this particular course. When we have a graph of ln of a function of x, right? That function of x could be x squared, it could be 2x plus 5, it could be it could be a cubic, it could be an exponential thing, it could be all sorts of different things. We have some common properties. Now let's talk about each of those in turn. So the first property is the graph of ln of f of x has got asymptotes when f of x is equal to 0 and when y is equal to f of x has asymptotes. If we think about the graph of y is equal to ln x, I'm going to draw this just off to the side here. That graph, I encourage you to draw it on your calculator, by the way. It gives us a lot of insight into what this function actually looks like. So the graph looks a little bit like that. It has an asymptote on the y-axis. It is undefined when x is equal to 0, and it has an x-intercept at x is equal to 1 because ln of 1 is equal to 0. So when we're talking about f of x being equal to 0, well, that's a point where we're trying to figure out what ln of 0 is. But ln of 0 here is the location of the asymptote due to ln. If f of x itself has got some asymptotes, then they will be reflected in ln of f of x as well. They'll appear there as well. The second property, ln of f of x exists only when f of x is greater than 0. This goes back to the graph of y is equal to ln x, right? This is only defined when x is 0. If we replace x with an f of x, then f of x has to be greater than 0. The third property, if our function has a local maximum or minimum, okay, now we haven't talked about this year yet. This is part of our applications topic, but I'm hoping you can remember this sort of idea from year 11 methods. If you've got a maximum in the original function, f of x, then you're going to have a maximum or minimum in the same location in the graph of ln of f of x. It might just be a little bit closer to the axis. Maybe further away, usually it's a little bit closer. Ln of f of x has got x-intercepts when f of x is equal to 1. Okay, if we have a look here, ln of 1 is equal to 0. That means we've got an x-intercept at x is equal to 1, and the graph of y is equal to ln x. All we're saying here is ln of 1 is equal to 0. So if f of x is equal to 1, then ln of f of x is equal to 0. Finally, if our function has a y-intercept that's a non-zero, and that's at a point y1, then ln of f of x will have a y-intercept at ln of y1. This is going to make a lot more sense when we look at an example like this. So what we can do, and you can see this in the handout, is we can make some statements about f of x and make corresponding statements about ln of f of x. So if we were to do that, let's draw up a little table here. Here we're talking about f of x. Here we're talking about ln of f of x. Let's run through each of these properties. Okay, the first property, we're talking about asymptotes. This graph doesn't have any asymptotes, right? It's a cubic. We can see that. We can see that it's got that cubic shape. No asymptotes present. But there are a couple of points where f of x is equal to 0, okay? Using our calculator, we see f of x is equal to 0 when x is equal to 0 or plus or minus 3. That means ln of f of x will have asymptotes, vertical asymptotes, at x is equal to 0 or plus or minus 3. Okay, what we can do is we can put those in as vertical lines. Okay, we know not to cross over these lines, so we won't. Okay, so I've drawn in some asymptotes there. That's point number 1. Point number 2, ln of f of x exists only for f of x greater than 0. Well, let's look at our graph. F of x is greater than 0 for 2 regions. We've got a region here between -3 and 0, and then another region here greater than 3. So let's write that. It's greater than 0 between -3 and 0, and x is greater than 3. Now in methods, a lot of the time, particularly when we're talking about functions increasing or decreasing, it doesn't matter whether we use strictly less than or equal to. This, however, is one case where it does matter. We're talking about f of x being greater than 0 for these domains. If we had all of those, then we're talking about these points here where x is in fact, or where f of x is in fact equal to 0. It needs to be strictly greater than 0. So we're talking about these regions, these domains, being strictly between the values. This means ln of f of x exists for x between -3 and 0, and x greater than 3. So that means we can block out these regions here. I may be doing this in a very light pencil, just so that I know that I'm not going to be drawing anything there, right? Our function's negative here, it's negative here, so ln of a negative doesn't exist, so the function is only going to exist somewhere in here and somewhere out here. Let's keep on moving. Number 3. Local max and min have got the same x coordinate. Well, there's only one x maximum, so one maximum point right there. So I know I'm going to have a maximum line somewhere. I'm not going to represent that as an asymptote. I might just do a dotted line there. I just want to make sure that I get a max in line with that maximum that already exists. Okay, fourth dot point. Ln of f of x has got x-intercepts when f of x is equal to 1. Now this graph doesn't have it doesn't have a y-scale. So I do need to be a little bit careful. What I can potentially say is, vaguely there is x is equal to 1. We can see a couple of points that are going to have axis-intercepts kind of vaguely there-ish. Let's just get rid of some of these, just so it's a little easier to see. Okay. So we're going to have 3 x-intercepts. That's, of course, assuming that 1 isn't, somewhere up there. We don't know what the y-scale is. We're making a bit of an assumption here. Step 5, if we've got a y-intercept, then we're going to repeat that y-intercept. Our y-intercept is just in here, so there's going to be no y-intercept for this function. Okay, let's get drawing. Let's start over on this side of things. This is going to be a little bit easier. We know that we're going through this point, right? We're assuming that's roughly where y is equal to 1 is, right? So we're going to do that. It looks like it's getting larger and larger and larger. So ln of x is going to do the same thing, but we do have this asymptote here. So I'm going to draw along the asymptote, being careful not to cross over it, trying to not wobble too much, and we get that line right there. For this section in the middle, we know we're going through these 2 points here. We've got a maximum kind of there-ish, and we've got vertical asymptotes as well. So our graph is going to look a little bit like that. Okay, what I'm going to ask you to do when you're working through finding graphs of ln of f of x, think very carefully about the graph of f of x itself and build up from there. Okay, I would suggest it may be really helpful to have a sketch of f of x onto which you are then showing me what ln of f of x is.